Thank you, Janelle. Good morning. I'm Grace Kang, and I'm Director of Communications at PEER, and I'm also the project coordinator, so it's my pleasure to moderate the sessions that will present more details about the project. So we'll just get right into it. We'll have time for a few questions after each of the session blocks, so please do submit your questions in the Q&A button at the bottom of your Zoom screen. Right now, we'll hear from Bret Lizundia, structural engineer and principal at Rutherford and Chekene, about the efforts of a workshop with claims adjusters. This workshop was designed to gather estimates of repair costs. Bret, please.
Thank you very much, Grace. Pleasure to be here this morning for those of you on West Coast time, or this afternoon and evening if you're somewhere else around the world. As Grace mentioned, I'll be talking about one of the interesting aspects of the project where we did a workshop, as we called it. It was actually quite a lot more than that, with claims adjusters to gather a whole host of information. And yes, I am advancing. Okay, good. So sorry, I'm having trouble here. Wow. Jasmine, are you able to reverse this? There you go. Thank you. It doesn't seem to go backwards for me. In any event, the goals of the workshop were several. First of all, we convened a series of experienced claims adjusters, and we wanted to gather their expert opinion on estimating damage to single-family wood frame homes. We wanted to compare the results if the building had been retrofitted versus not retrofitted. And we wanted to drill down into understanding what kind of assumptions they use, what the industry practice is among their colleagues. And ultimately, we wanted to compare their results against the FEMA P58 methodology, which is underlying the approach that we took analytically. So in terms of what I'm going to cover this morning, I want to review the scope of the study, what all was involved. We had a key workshop online where we brought everyone together and we talked about issues of differences, and we made decisions on how we were going to address those. Then I'll show you results of estimates and then draw some conclusions and make some recommendations. So let's first talk about this package, the damage description package that we issued. These were the rules of the game, the instructions to adjusters on what we wanted them to do. And this document grew and grew as we delved more deeply and had more reviews of people. It covered the buildings, and I'll show you those in a minute, that we were estimating, the damage to those buildings, the different scenarios that were considered, and a very detailed set of assumptions to kind of establish the context and how we wanted things structured. CEA suggested that we use the Verisk platform, which is common in the industry. We're not endorsing that in any way, but it provided for kind of ease of use and efficiency and commonality amongst the estimators and adjusters so that they were all doing a similar approach. This all got combined into several things. One was this 106-page damage description package. We also had a questionnaire that we did through Excel, and then we gave them the starting point of Exactware files to kind of save them time so they didn't have to build the basic geometry of the building in there. This was reviewed by a number of members of our project team. We have a peer review panel. We actually engaged, at CEA's request, kind of an expert user of that particular software and somebody who advises a number of folks in the industry, and his assistance was greatly valued. And then CEA as well did a detailed review of this. So we had 3 buildings. The first 2 are very similar in terms of geometry, at least. 1-story, rectangular house, 2-foot cripple wall. The main difference is finishes. This was intentional so that we could kind of gather information on how costs differ between stucco, between lath and plaster, horizontal siding, gypboard. And that was quite useful because the FEMA P58 methodology has limited information on lath and plaster effects. So we've had to kind of develop those to some extent from scratch. We could, though, compare directly other things. So the third building was 2-story. So kind of similar in terms of the basic footprint. We added a garage to it. It's got more modern T111 plywood on the outside, and then kind of interiors chipboard. We also made it a tall cripple wall to see if that would produce any differences. So for each of these case study buildings, we just created 4 damage states. So, you know, deliberately colored them in sort of ATC 20 post-earthquake evaluation colors. So damage state 1 has damage, but it's something that would receive a green tag. So we would call that cosmetic repair, fairly limited work. Damage state 2 is more significant. You might receive a yellow restricted use tag. We've got a lot of finish damage at that point, but nothing really significant on the structural side. And damage state 3, there's a big chip. That's where we really started having significant damage to our cripple walls. We've got permanent residual drift. We're worried about gravity load carrying capacity, and substantial damage is occurring in the superstructure as well. Damage state 4 was defined as so bad that we're going to replace the building. So you can see how they step up. So with each of those sort of abstract descriptions, we then had detailed pictures in several different ways. So we have these crack maps and spall repair maps where we define the length of cracking, the amount of spalling that was happening on each exterior facade. We have similar descriptions for interior partition damage. We talk about what happens to the floors and the walls and the tile, MEP systems, a whole series of categories. We tried to include photographs, usually extracted from the literature, and to just kind of illustrate the extent of how bad that damage was or wasn't. So we had that all assembled. We sent it out to our adjusters, and we then convened first a call with them after they'd had a chance to dip in and take a look and get a little overwhelmed by how much they had received. We took their questions, we tried to answer initial questions on that, and then they were off and running. So they prepared their additional estimates and sent them to us, and then we poured over them. We looked for issues, commonalities, questions, things that could have been clearer, areas where there are differences in the approaches that each adjuster and their firm takes. And we had I think, very successful workshop where we had a good group discussion amongst a diverse audience of how to address those. And then we kind of redid it. So there was another round after the workshop with a much more detailed damage description package that described the decisions that were made and how we wanted them to address that. And then we got a second round of estimates back, and we again poured over those and organized them and processed results. So the scope, I mentioned that Chris McDermott was an advisor. We had 10 adjusters who do earthquake damage and many other kind of catastrophe damage estimating, sort of a powerhouse group of adjusters. These were quote unquote volunteered by their firms with nudging of CEA, and we're very grateful for that. I could obviously not have done any of this without them. So in terms of permutations, if we have 3 kinds of buildings, retrofit, unretrofit, 4 damage levels, in theory, there's 24 scenarios that we would have gotten estimates on, but some of them are awfully similar to one another. So I combined them to kind of reduce the effort, but it's still kind of a dramatic amount of work. So if we have 5 adjusters doing a certain set of scenarios sort of in total, out of the 10, we sort of split up so everybody wasn't doing everything. Then in theory, we would have gotten 85. We were pretty successful in getting almost that amount, and I feel pretty good about that. But you can imagine this is, sort of a tip of the iceberg of the total amount of adjuster estimates that have been done in the industry, but it's a focused one. So once we had all that information, it was a little staggering. You know, the Xactimate report files, you know, are on the order of 30 to 50 pages, depending on the scenario, each for every one of those scenarios for every adjuster. So it's thousands of pages. And we made a decision early on with Chris's help to kind of combine things into categories. So these are the categories that helped us summarize and condense, you know, several pages of the detailed work that the adjusters were doing. So we had a cripple wall category, we had an exterior and interior category, windows and doors, ceilings, floors. You can see the list there. So that was more helpful in kind of helping us review things between folks rather than on the detailed, you know, 40-page line estimate level. So what did we find when we brought everybody together and initially and had looked at that first round of things? So what we saw is that there were some places where our descriptions were on target, no issues, everybody agreed. There are other places where we decided if you've got stucco damage on the outside, then we're going to take it off, and the water barrier underneath that's exposed is going to be completely replaced and patched. Maybe even more significantly, if there's tile somewhere, then we're going to assume it can't be patched, and that room, it's going to get full replacement, even if only a portion of that was damaged. That is kind of general industry practice and has a big impact on costs. So even if you know, structurally there's not a lot of damage, the cost of tile replacement can be fairly significant. Leaning cripple walls, you know, which is kind of a very key aspect to many areas of this project. We had a lot of survey questions about what would you do in this situation, what would you do in that situation. It turns out that there is not industry consensus on this, and many of the adjusters' general approach is to defer to a structural engineer that their firm kind of hires to come in when the damage is significant, and that made things difficult to cross compare. So we made a decision to direct them to make certain assumptions. So we added additional language, you know, as I show here, of what to do in these three damage states to basically tell them what to assume in terms of the repair. We also had instructions, you know, as a practicing structural engineer, I, you know, routinely assist and review cost estimates for my projects. Those aren't buildings necessarily that are built yet. You know, this is an estimate in the future. So typically costs are escalated to the midpoint of construction. This turns out to be a very unfamiliar concept in the claims adjuster world. They just don't use escalation, it turns out. They are kind of doing things in real time. They might have multiple estimates as more information comes in, and the costs are sort of done at current dollar values. And that was news to me. I didn't realize that was the approach, and shows really a pretty fundamental difference between different industry groups and how they deal with inflation and escalation. We also made decisions about what contingencies to assume that might come up with changes when you get into construction. We had advice about how long the building was going to be in or out of commission, depending on the damage state, ranging from 2 weeks to a year. You know, pretty dramatic difference between damage state 1 and 3, for example. We made assumptions, or sort of directed them to certain things about architect and engineer design fees, plan check fees, special inspection, which is pretty rare for a house. Some jurisdictions do a little bit. So those were imposed on them. Originally, we had asked them to tell us their assumption, and we didn't get a lot of kind of good response on that. So we ended up deciding to define it. A big thing that has grown in California over the last, many years is the cost impact of dealing during repairs with lead paint and asbestos. And I did not appreciate how significant this has become. So we had a lot of debate in the workshop about how to do that, and we ended up making some decisions related to the different damage states based on their experience and what they see. So these are weighted averages. They certainly see, way higher values in some, extreme examples than, way more than 10,000. And then they see less, but typically they're dealing with this, and this has become kind of a growing, challenge, particularly in California. We decided in the end to exclude what's called coverage C and coverage D in the industry, personal property and ALE, for simplicity. Okay, so those, and there were more. That was sort of highlights of decisions we made. But let me talk about results next. So the first thing that we did is we looked, in my office with the folks who were helping me at what we got. And despite, all of these review steps and instructions, and we had cheat sheets in the damage description package about where to put things, this is hard. I was sort of impressed by how tough it is to be an adjuster, and the challenge and the really intense detail that the programs and the work that they do go through about all the very specific choices. So when you kind of step back and try and aggregate that and say, we wanted you to put that particular thing in miscellaneous rather than indirect, that wasn't necessarily how they did it. And so what we did, just to make things more comparable, is we moved values from one place to another, depending on how we had originally intended the value to be located in which category. We didn't change the number. So, the bottom line total is the same. It just made it a little more easy for us to compare individual categories. Not everybody resubmitted. And so we adjusted the ones that didn't resubmit values to include any decisions on specific things that they needed to do with indirect costs in the end. Okay, so with that being said, here's some comparisons. So CS1, that's case study building 1, that's that 1-story house. And you can see the damage state 1, DS1, starts at $15 a square foot. These are in last year's dollars. And then the replacement value of that house, about $240 a square foot. So, not surprisingly, the more damage you have, the more it grows. And it grows fairly significantly with each damage state. So we actually kind of liked the way we had divided up the damage states. We got kind of a nice variation that really reflected meaningful differences. There are some differences on a dollar per square foot basis between the 3 buildings, but not a huge amount. So that was, interesting, that even though we had all these variations at a bottom line aggregate level, they're not dramatically different. And you can see on the bottom row how the mean values of all the adjusters who worked on a particular building type, what they came up with. So we also, here's one snapshot of one particular category, indirect costs. We have them for cripple walls, we have them for other subcategories of the total, but you can see how indirect costs, which are overhead and design fees and plan checking and permitting and things like that, are represent 10-15% of the total, which feels about right to me based on my experience. So another really important thing we did was to compare the differences between what the adjusters were submitting to us versus the FEMA P58 methodology. So Dave Welch and Greg Deierlein, who we're going to talk later, kind of were in charge of that effort. And so you can see on the right, mean and mean +1 and -1 standard deviations on their work, and how that nicely envelopes the adjuster values. Pretty impressive, really, in how similar the ranges were between these, and quite reassuring to us that we were on the right track. If we compare mean values directly, so there's a lot on this slide here, but basically the blue and the gray are case study building 1, and 1 is the adjusters. That's the blue, $15 a square foot here. The P58 result, $19. So these first 2 guys pretty similar, 7 and 4, maybe a little different, but sometimes one's a little lower, sometimes one's a little higher, but pretty similar. So again, we didn't see a need after this to make any significant changes in the approach that we were taking analytically. So we have coalesced all that information, put it together in data that will be available to any researchers who might be interested. It has 4 primary Excel spreadsheets that compare a whole host of different things and have histograms and summary tables, more information that is in the published report that will also be issued. So for those people who might want to dig into that, it's available. It is by agreement, prior agreement with the insurers, anonymous, so only I know and my staff knows who was who, and we're not giving out the Xactimate files for similar reasons, but there's still a ton of data that anybody could dig through. So conclusions and recommendations I'll wrap up with. So in terms of conclusions, as I mentioned before, reassuringly and sort of impressively, adjuster estimates in the P58 were awfully similar. You really have to have detailed estimating assumptions. I thought we were super detailed, and then we had the workshop, and despite all these reviews of a whole host of really talented people, we still needed more. The adjusters were always wanting more to make their job, more rigorous. So it's a testament to their professionalism, but it's also a lesson on, different assumptions can make a big difference. I came away feeling that the world that I typically live in as a design professional and the cost estimates that I do, as opposed to what the claims world does, as opposed to what sort of academic researchers do and what catastrophe modelers do, it's almost like we're all talking a bit of a different set of language with a bit of different terms. The fact that some adjusters had never even heard or used the word escalation was kind of amazing to me. And there were other things. So I think that a project like this sort of highlights the commonalities and the differences, and I think helps each of us understand one another better. So you got to be specific. And we, in working with the modelers who were on the online workshop, we decided to exclude demand surge, sort of things that change when there's a lot of damage happening after an event. Catastrophe modelers, as I understand it, do that separately anyway. So we took that out as an assumption. Things that will occur in some small subset of buildings, legal fees and radon and mold, we excluded. So in some ways, what we have is a bit on the lower bound side, but you can't kind of cover all of these different permutations. So in terms of recommendations, we felt that the only real significant area where we wanted to drill down, and we were able to use the adjuster values to do that with the lath and plaster estimates that we got. So in our report and in the work that we did with Greg and Dave, we were able to cross-compare adjuster values on lath and plaster versus chipboard. So that was a kind of a great benefit as they got specific on how they were going to deal with that in their many permutations. Again, and I keep saying this, but I want to keep saying it as well. When you do this, you need to be really, really specific about what you're assuming. Over and over again, it was kind of brought to bear that you just can't do things without having this be clear. It will be apples to oranges by definition. And so when you look at things in the future, other projects, or as people are crafting projects, I really want people to have 100-page descriptions of assumptions, because if you don't, you're just kidding yourselves on whether you're actually getting really good information. I think there's a need to study lead paint and asbestos abatement as it relates to earthquake damage repair in more detail. There was a lot of great knowledge in the community about this, but there was also a lot of variation. And I think this is an area where we can help one another more to better understand this, and that's because it's a big cost. It's worth obsessing about because it has a big impact on what people pay. I'll put in a plug, but it's a well-deserved plug. So, one of the rules of the game for our instructions was that the EDA 2 guidelines that Curie had produced, a while back are definitely industry standard practice. And we said, follow that, wherever possible, that's your guide. That has been out there a long time, and a recent ATC project, updated these to two wonderful new documents. So they will become now the new industry standard, and we definitely encourage that. So remember, I was mentioning that we couldn't get really agreement amongst the adjusters on how they dealt with leaning cripple walls, and at what point they repaired them, what point they jacked them, what point they replaced the cripple wall itself with the building kind of up on shores, and at what point it was so bad that they ended up having to replace the whole building. So that's an area where more detailed work, between engineers and adjusters needs to be done. And finally, other people have said this for sure, but I really believe this is true. Trying to get it to happen is the challenge. So insurers have payout information that is, of course, proprietary and something that's of great value to them. But if we had that in some anonymous way about what's actually paid out, you can imagine how valuable it would be to kind of improve FEMA P58 or similar projects. And if there's a way that we can work together to kind of share some of that information, I think that it will benefit everyone in having kind of better research, better analysis, better pricing of insurance policies. So I will end here. I think I'm on time, and turn it over to our next speaker.
Bret, thank you so much for that very enlightening presentation. A lot of lessons learned about costs. So at this point, we'd like to hand it back over to Janelle to ask a little bit about you, our attendees.
Right. So now that we've got, I think everybody is awakened and tuned in, if you could please click on the title that best describes what you do and your professional level. It's very useful to presenters, particularly since we can't see our attendees, so that we understand who we're speaking to. So if you could take just a few seconds here to tell us who you are, and in just a second we'll put up the results, and we can also compare it with yesterday. I know we have a lot of repeat attendees, and we thank you for being back with us. So couple more seconds, and okay, Jasmine, why don't we show what we've got? Oh, interesting. It is a little different than yesterday. So academic researcher seems to have pulled into number one, but of course CAT modelers, and then the insurance industry well represented. And thank you, engineers, for joining us today. So thank you. So interesting information for our speakers, and I'll now hand it back to Grace and we'll continue. Thank you.
Thank you so much, Janelle. We will proceed with our next presentation about the computer modeling and analysis process, which was used to develop the damage functions for the unretrofitted and retrofitted crawl space construction. This presentation will be presented by Dave Welch, postdoc researcher at Stanford University, and Greg Deierlein, professor at Stanford University. Dave, please proceed.
Okay, thank you, Grace. Yep. Okay, there we go. Not sure if that was the mouse click at the arrow. Hopefully we can do this. Yeah, so as Grace said, my name is David Welch. I've been working with Greg Deierlein, doing all of the numerical and analytical work on the project, and also just really trying to work as much as we can with all of the other great working groups that we have, as we kind of represent the kind of the end of the funnel, trying to bring together all of this great information we're putting together. And I'm going to try to give you a little taste of everything behind the results before moving on. So just as a brief outline, I just want to transition a little bit between the FEMA P1100 document serving as the retrofit criteria for this project, and then moving into the objectives of the new project. And then my portion of the talk will be going over the FEMA P58 process, as Bret even somewhat introduced when discussing the workshop. And then I'll show this more graphically as I go through, try to give a little bit of the background behind this whole process. And unfortunately, I won't be able to get into every single detail, but we do have a 400-page report that has every input value and assumption made for all this work. So anyone interested in the real nitty-gritty can obtain that once that's published in the near future. Then after going through that, I'll turn it over to Greg, and he'll talk about some key results and findings, and then conclude our talk. So as Kelly mentioned yesterday when talking about the ATC 110 project and the FEMA P1100 document, this represents the engineering solution to the crawl space vulnerability problem, where now is a stepping stone where we have the pure CEA project, where this work is aiming at quantifying performance with the intermediate step towards the bigger picture of just hopefully implementing more of these retrofits and reducing the vulnerability of these structures. And so one key difference in these between these two projects was the development of the retrofit guidelines focused mostly on a very high seismic demand probability of collapse at the MCE level. And this used the FEMA P695 procedure, where doing incremental dynamic analyses and all the appropriate adjustments, we can estimate what the probability of collapse was at the MCE level event. And then in addition to probability of collapse at the MCE level, of R factors with different considerations rather than just the nominal P695 collapse probability. And this relied heavily on understanding shifting drift into occupied stories, and importantly, the constructability of these different retrofits, trying to make a balance between the collapse reduction and also and how many of these retrofit details will actually fit in most houses. So that's just a little recap on. Oh, is that moving? Oh, okay. Okay, and then so now obviously, as everyone that's been here for the last 2 days, we know that for the new project, we're attempting to develop loss functions to quantify the benefits due to retrofitting in terms of reducing the risk of collapse and economic losses. Where the main question shown in the top bubble is trying to understand how the removal of the cripple wall vulnerability due to retrofit changes the risk of loss. And then in order to do this, oh, and I see people say my audio is warped. Now I'm going to try to speak a little louder and closer to the screen. So in order to do this, oh, there's. And maybe I can stop my video and the audio would be better. Okay, so hopefully connection's okay. We are using the FEMA P58 approach, and this really, this slide here really paints the picture of all of the collective effort that we have to achieve to our project goal.
Hi, this is Janelle. Obviously, we have some sound problems with Dave. We'll give it just a second, and if we can't get him to maybe phone in, we can always move to the next presentation. So hang on for just a couple seconds, please. Once again, if you just joined us, we are having some sound problems with our speaker, Dave Welch. We're asking him to call in. Ah, he's back. Dave, can you do a sound check?
Okay.
right.
Well,
Dave, you're muted. Can you do a sound check, please? Okay. Grace, can we move to Evan and then we'll get back to Dave?
Yeah, we could do that. The other option is I could try to wing it. I've worked on this with Dave. I've prepared the second half of the slides, but I could walk through these if you'd like. But
Yeah,
or we could go to Evan, either way.
Go ahead, Greg, why don't you proceed with this, because we're right in the midst of this topic now, so please proceed.
Thank you.
Okay. Yeah, and if Dave could jump in at any time, he's welcome to have it back. So, Jasmine, can you give me the controls? Maybe you've already done that, maybe? Yeah, okay, there we go. Okay, so as Dave was presenting, we've the results here are all based on this detailed P58 procedure, which again, we're taking variants of the houses, we're taking the ground motion, Sylvia spoke about those yesterday, running them through structural analysis models with open Cs, and then using the P58 methodology that, given the drifts and probability of collapse and so forth, we're calculating the losses on the house. Oops, let's see if I go forward. Apologize, trying to get this slide to go forward on me here. Oh, there we go. Oops, too fast. Okay, and in terms of the number of variants, I think Evan might have talked a little bit about this yesterday, but we looked at 1- and 2-story houses. We looked at 3 construction eras. The bookends are like pre-1940 versus 1956 to 1970. The major difference between those two was really the interior wall material, whether that was lath and plaster in the older houses versus gypsum board on the newer ones. The intermediate 1940 to 55 is really a mix of those two construction types. So we really did analyses of the older and the more modern houses. In terms of exterior material, we looked at 3 types: horizontal wood siding, stucco, and T111. And then we looked at a few variants of cripple wall heights, and including the stem wall. And in terms of the index building that we analyzed, we really made use of a lot of the work that was done previously in the ATC 110 project as part of developing the retrofit guideline. That is to survey old historic houses and to look at the typical geometry of those. What's the density of interior walls? That is, how many interior walls for the amount of space that you have. And this was all then built into our model. So in the right-hand side of this slide, you see kind of a representative configuration in terms of the floor plan of the building and the number of walls, and the rough size is roughly 30 by 40 footprint. We obviously made use of a lot of the testing that you heard about yesterday, which was primarily focused on looking at the behavior of the cripple wall. There's been quite a bit of testing on wood frame structures in general, but not as much of the cripple wall. So again, won't go over all the details that you heard yesterday, but making use of the smaller individual wall panel test down at UCSD, and then the larger component test that included both the cripple wall and the first floor above that run at Berkeley. And you probably, this is a repeat of maybe a slide that you might have seen yesterday, but just showing the dramatic improvement that you could get in terms of the cripple wall behavior between the retrofitted and the unretrofitted cases. So this is just kind of one example, but these were things that David went through very carefully in developing the computer model, or the parameters for the computer model that we used in OpenSeas. So you see the case there of the existing with the stucco, and then when we add the structural wood panel behind it, the dramatic increase in strength that you see. And in fact, the increases, if we showed you the wood panel siding, that would be even a larger increase, because those were the wood siding was the most vulnerable cripple wall. you heard about yesterday the ground motions that Sylvia and Josef Bezorgnia developed. They actually looked at 10 sites. We picked out 4 sites to focus on. Those are the 4 that are shown here, kind of a low seismicity, Bakersfield, higher seismicity, San Francisco and Northridge, which are somewhat comparable, and then the worst site of all, the San Bernardino. Now, apart from the ground motions and the characteristics at these different sites, why these were picked is how they related to the P1100 retrofit. So for the typical plan sets, what's shown on the right there is that there's kind of 3 standard retrofit designs depending on the design basis ground motion. So at the lowest level, a design of SDS, short period spectra of 1G, and then going up to 1.5G. And those 3 tiers there that you see, that's the amount of retrofit that you'll have. So while the existing houses that we looked at were the same in all 4 sites, when we looked at the retrofit of the houses were different. In other words, the buildings in Northridge and San Bernardino used the highest retrofit, the 1.5G. In fact, San Bernardino, the seismic hazard there even exceeded that, but that was the maximum amount of retrofit. And then going down to Bakersfield was at the lower end. In fact, in Bakersfield, the retrofit was a little bit over-designed for the site, the standard plan retrofit. Okay, and then the ground motions themselves picked up the characteristics I think Sylvia described. We used suites of ground motions, 10 stripes, if you will, ground motions of different intensities that were conditioned on a short period, conditioning period of 0.25 seconds, which is capturing the spectral shape as it changes as we go to higher and higher intensities. Okay, and this is just what's shown on the right there is the example for the San Francisco site. Let's see if I can go forward. Okay, then this is a schematic of our open seas model. So it has I mentioned before, the kind of the index building layout of the house and how many exterior to interior walls. So you see the idealized floor plan that shows there. So we translated that into open seas models. These are 3-dimensional models where we're representing the floor with a rigid diaphragm, but then between the floor diaphragms, there's shear springs that are representing the interior walls, the exterior walls, and then down in the cripple wall below the first framing level, we're representing the perimeter cripple walls and then the retrofit on top of those. There's also the P delta effects are picked up in this. That is, as the building displaces laterally, we're picking up the story height effect. And so you could just see a schematic for these shear springs, for example, representing down below the first floor the behavior of the cripple wall, and then up at the first floor representing the interior and the exterior walls with the different materials. Okay, and this shows an example of the very careful kind of development of the hysteresis models, and we used kind of 2 springs that were in parallel with each other, and we investigated various different options, but this is the one that was able to pick up, both the high stiffness in the beginning of a lot of these materials and then how they would degrade and the pinching effects. And the hysteresis plot you see there is a comparison between our numerical model and some of the experimental test data. These were the cripple wall tests down at San Diego. So we feel we went to great lengths to, make use of all the test data that was generated as part of the CEA project, and also going through the literature for the superstructure materials, digging back into even some older tests on some interior plaster walls and the wood and stucco siding. This just gives an example of some of the data that was harvested. Kelly Cobean actually helped quite a bit on this because a lot of this data was actually collected as part of the prior ATC project. So going through past test reports, again, this was for more of the superstructure material. And there's quite a bit of variability there. So we used kind of judgment in trying to get characteristic values and then look at the variation of the expected strength and doing our best to get the backbone curves and then to characterize the hysteresis behavior. Okay, the next thing we had to do is to look at damage. So we've gone through the computer modeling, and that was just the tip of the iceberg. But then once we run analyses and we get deformations, that is drifts that are in the cripple wall or drifts in the superstructure, then how to relate that to damage in the structure, and then finally to the cost. And for this, we really utilized all the work that was done previously that's in P58. So there's a database of many different types of materials, gypsum, wallboard, lath and plaster, exterior, and the different damage states we have there describing on these plots you see drift ratio versus the probability of being in different damage states. So we went through those carefully. We made some modifications based on some of the data that came out of the CEA testing, in particular large-scale tests that were done at Berkeley. So some adjustments to these damage functions from P58. Okay, and then the next thing, given the damage and the damage states in each of those walls, then to go to cost. And here again, we relied on pulling out data from P58. There were cost estimators that contributed to those functions. So we have, for the different damage states, in exterior walls, interior walls, and also looking at different interior wall finishes, whether it's kind of a standard finish or whether it's a high-end ceramic tile finish, say representing the bathroom and kitchen spaces in the building. Okay, so those are the cost functions we started with. And again, we kind of went through those carefully. One of the things, if you're familiar with P58, that deals with a whole spectrum of buildings of different size that thinks about the number of units that are in a house. In other words, how much material is being replaced. So we kind of went through those carefully and made sure we made adjustments to them that were appropriate for the index type of houses that we have. Now, as Bret mentioned just previously, we had the detailed cost adjuster damage workshop. So that was like a totally independent way to assess these repair costs. So we began with the ones from FEMA P58. And then working with Bret on this workshop, we kind of hypothesized these different buildings and being in different damage states. We then calculated losses, repair costs based on P58, and then comparing it with what came out of the adjuster workshop. And these are just some examples. We have, these are kind of documented in our various reports, but this is showing one of the 3 case study houses that Bret introduced. And it's just showing the results for the so these are looking at the 3 damage states. So they're going across this plot here, 1, 2, 3, 4, 5 on the bottom. Those are 5 different adjusters. The percent replacement cost is on the vertical axis. And the 3 bar graphs in each set refer to the 3 different damage states. So the ones shown in gray color are the adjuster values from the 5 adjusters, and then getting mean values of those. And then we compared that to the P58. So you see the mean from the workshop shown there for those 3 different damage states. These losses, as we go through, by the way, are all based on percent replacement cost of the house. And then comparing that to the numbers we had from P58. And in general, we were pretty pleased that the P58 numbers, totally unadjusted, tended to agree pretty well with the data from the adjusters workshop. And you also see in this picture, which was representative of the other 2 houses looked as well, that just between adjusters, there was quite a bit of variation in how they would judge the losses. So I think when you look at the P58, while the mean could be somewhat different than the mean from the workshop, that it's right there in the mix in terms of what adjusters would have estimated for that house. Okay, and then another aspect was to look at the replacement value of the house, because the P58 numbers and from the adjuster workshops, those looked in terms of real dollars in terms of what different repairs would cost. We then, when we looked at our damage functions, we normalized all these in terms of percent replacement cost. So here again, we looked at replacement costs for the 3 case study houses, and roughly you see the numbers there all around $200 per square foot. So in fact, that's what we used going forth when we looked at, say, the loss due to collapse of a house. That would be the full replacement value, $200. And also when we took the repair costs from FEMA P58 and normalized them, we feel this $200, while it might not represent the cost of a house in downtown San Francisco, it's commensurate with the estimates of the repair cost in an average sense. Okay, and that's just showing the workshop mean and the P58, what we're assuming. Okay, another big assumption we had to make, and it was quite a bit of discussion within our group and with our review committee, is what's the amount of loss if you have the cripple wall collapse? Because there was nothing in P58 that covered that. And in fact, even talking to the adjusters, not a lot of information back on that. But there is some work previously, the Curie Caltech project, Keith Porter and others worked on this, that had kind of a mean value in there that was predicting roughly 33 or 1/3 of the replacement value. That would be the loss due to collapse of the cripple wall. There were other practitioner surveys, which are shown on the right of this slide, the lower right, which went from that kind of 33% loss value all the way up to 100% loss. So with a lot of discussion, we've decided amongst our team to use 2/3 of the replacement value, or 67% of the replacement value, attributed to when we have a cripple wall failure in our study. We do have numbers calculated for the lower 33% and the 100%, but the results we'll show today is based on that 2/3 value. Okay, so that summarizes Dave's first part of the talk. I probably went through it a little quicker, maybe leaving out a couple of details, but maybe Dave could get back on the phone if there's questions later. So I'd like to transition to just look at some of the results we have from these detailed analyses. And in starting this out, I'd point out that there's quite a bit of data that was generated. In total, we developed 250 damage functions. That's basically 125 pairs of damage functions. That is the house with and without, or the original house, and then the house with retrofit. So there's 250 of those damage curves. Behind the scenes on that, there's quite a few analyses. For each of those 250 damage curves, we did the OpenSeas, the nonlinear dynamic analyses, 3-dimensional, with 10 stripes of earthquake ground motions with 45 ground motions per stripe. So in total, there's about over 100,000 nonlinear dynamic analyses that were done. You could probably double that number if you, in fact, include some of the parametric studies or some of the interim results we did along the way. And then from those, the results of those nonlinear dynamic analyses fed into the P58 calculator, which is doing Monte Carlo simulations on the damage realizations and the loss realizations. So there's millions there. So what enabled us to do all these analyses was building a computational workflow. I won't go through all the details here, but just to point out, just the runtime itself was, many months involved with that. And all of this data, apart from the 400-page report, we have all the data that came out of these studies, not only the damage curves, but some of the components behind that, has been compiled and turned over to CEA. So I'll just be, in the next few slides, just summarizing some highlights from the results, certainly not all of the 125 pairs of damage functions. The one I was going to start with here, just as an illustrative example, this is a 2-story wood siding building, as you've seen from the little graphics. And we'll look at the existing and the retrofit condition. This is a post-1955 era, which really means it's going to have gypsum wallboard interior, has 2-foot cripple walls, and this is one who's located in San Francisco, which is going to dictate then the strength of the retrofit that we put into it, in addition to using, when I look at expected losses or the design level ground motions, the San Francisco site. And this 2-story example, this is probably 2-story with wood siding. This is one of the more vulnerable houses that, on the flip side, benefits the most from the retrofit. And as we look through some key performance, we'll look at the probabilities of collapse. We'll look at the damage functions themselves. That's the expected damage versus the ground motion shaking. And then we'll also look at some kind of statistics, expected annual loss or average annualized loss, and also the mean loss as a kind of a 250-year ground motion shaking intensity. This is kind of a characteristic one. It's a little bit less than the design value ground shaking, but it might be one if you're looking at resilience of a community, that 250-year intensity. So just a little bit behind the scenes of what goes into these calculations. So this graphic on the left is showing the intensity measure of the ground motion, that spectral acceleration at that 0.25-second period, versus the story drift ratio. And at each one of those levels, we applied 45 ground motions, again, with the conditional, chosen to match the conditional spectra. So 10 stripes, there's just 5 that are illustrated here. But then for each of those intensity levels, we would record what's the peak story drift that's happening in either the cripple wall or one of the first or second story. But then also at increasing intensity, the drifts get so large that it's going to cause collapse. Typically for the unretrofitted, it's going to be in the cripple wall. Otherwise, it could be in the first floor of the building. But looking at the collapse. So at each intensity level, we kind of separate the response into the collapse cases, which has one loss associated with it, and then the non-collapse cases, which are evaluated with the P58 procedure. And for the cases that have collapse, we could take the plots that correspond to collapse from the left plot and create a collapse fragility curve, which is plotting the probability of collapse versus the ground motion intensity. And we used kind of median models, but then we did add in some modeling uncertainty into the collapse fragilities. Okay, so for that 2-story wood frame house, what's shown on the left slide here are the probabilities of collapse under increasing ground motion intensity. And so, for example, if you look at maximum considered earthquake ground motions, a very high level, you see that in the unretrofitted cases, the original one, very high probability of collapse. And as shown by the graphic in the center, that collapse is always occurring in the cripple wall, very weak wood siding cripple wall. If we retrofit that, you see the probability of collapse drops quite dramatically down to a 22% probability at the MCE. Now, as shown in the graphic in the center, in fact, for this wood frame, this wood siding house, once we retrofit the cripple wall, that a lot of the collapses actually propagate up into the first story. I should point out this was kind of unique to this wood siding case. It does not happen as much if we look at the T111 siding or in the stucco. But the wood siding, once we retrofit that cripple wall, tends to push the collapse up, but admittedly it's at a much lower probability level. And the 2 plots on the right are just showing the drifts up the height of the house. So the first plot in the center there is looking at the existing condition, where pretty much all the drifts are occurring in that crawl space region. The rest of the house is going for the ride, if you will. But then once we retrofit it, we could see how we really limit the drifts in the cripple wall. But then at higher and higher ground motion intensities, you do get more drifts in the superstructure and primarily in the first floor of the 2-story house. Okay, now we just looked at probabilities of collapse. Here we're going to look at losses, or the damage functions. So on the plotted on the vertical axis is the loss. This is in terms of percent replacement value, and on the horizontal axis is the increasing ground motion intensity, again, spectral acceleration. Now the plot on the left is showing the existing house condition. And you notice here that a couple of things. You could see that the total loss number, it tends to saturate at around 2/3 of the replacement value of the building, and that's because basically we're getting failure in the cripple wall. And as I mentioned earlier, we made the decision that failure in the cripple wall would be associated with 2/3 of the replacement value, figuring some houses it'll be a total loss, other houses could actually be, through jacking and everything, brought back and repaired. But the other thing you see in the left-hand slide plot is that the total loss is entirely associated with collapse of that cripple wall. Now, in the retrofit case on the right, you could see that the loss curve, number one, the total, the blue curve there, is decreased quite a bit from the one on the left. And we deaggregate that into the different components. And you find in the retrofitted case, about half of the total loss is still associated with collapse. This, in this particular case, would be in the first occupied level, the first story. But then the other amount of that loss is the non-collapse case, is just damage to the superstructure. But for example, if you look at some from these damage functions, and this is one of the key products of our project, turning those over to CEA and then the companies that do loss modeling to come up with insurance rates and so forth, the damage functions themselves. But we also looked at some statistics. So again, this house is in San Francisco, assumed to be in San Francisco. And if we look at the loss under this ground motion with a 250-year return period, we could see for the original existing condition, it's about 56%. And under that same ground motion shaking, it reduces to 15%. So if you look at that difference between 56 to 15%, there's a 40% difference in replacement value. And for this house, the replacement value is on the order of $500,000. So that's roughly $200,000 less damage in the house by virtue of the retrofit at this ground shaking level. Another statistic we could look at is the expected annual loss, or sometimes called the average annual loss. This is where we're going to take these damage functions and integrate it with the hazard curve, the frequency of earthquakes that are occurring at that site. And if you look at the numbers, the expected annual loss for the existing case, 1.35% down to 0.27%. So roughly a decrease of 1% in expected annual loss. And again, if you translate that to dollars, that would be on the order of $5,000 difference in the expected annual losses. And you see in those little pie charts that are shown there, in the existing case, pretty much all of that loss is associated with the collapse of the cripple wall. Whereas if you go to the retrofit case, it's kind of a mixture of some collapse in the first story, but also other cases where you're just going to have damage both to the interior and exterior wall, showing blue and green to the kind of the damage for the non-collapse cases. Okay, so if we look at a slightly wider group of houses, so we're going to compare some 1- and 2-story houses with wood and stucco exterior. We'll start out by looking all at the post-1955 era. So all of these houses that I'll show in this segment will be gypsum wallboard interior with 2-foot cripple wall, and we'll stick with the San Francisco site for this example, looking at those same 3 metrics. Okay, so just comparing 1- and 2-story for the wood siding cases, and again, these are ones that have that very vulnerable cripple wall. So shown on the left is the 1-story case, where on top is the existing and down below is the retrofitted. So you can see for the 1-story example that by the time you retrofit that cripple wall, the probability of collapse, or the collapse at any one of the different ground motion shaking intensity, is practically nil. On the other hand, if you look at the 2-story house, that's the one we've looked at previously, we could see how a very high probability of collapse in the existing condition, but then when we retrofit it, drops dramatically. But under the very high ground motion shaking intensity, as those little red bar graphs shown in the lower right, we still get some collapses, but at that point they've migrated up to the 1st story. So this is the collapse behavior. Next we'll switch ahead to look at loss behavior between these different houses. First, if we look at the 1-story variance, this is comparing a 1-story house with wood siding with stucco, where we're looking at the damage functions, again, percent replacement value loss in the vertical axis versus ground motion shaking intensity, that you see that in general, the houses with stucco siding, this is in the existing condition, tend to be less vulnerable than those with wood siding. Okay, and if you look at the expected annual loss resulting from those damage curves, you could see shown on top, that would be the wood siding shown in orange and the stucco shown in green. Roughly for the stucco case here, it's about half of the expected annual loss for the stucco siding case as compared to the wood siding. And that really results from the fact that the cripple wall for stucco, provided it's in reasonable condition and attached, that it's an inherently stronger cripple wall than you would get in a wood siding case. And that translates into the loss at the 250-year hazard. And then if we check out the retrofit for both of those, the retrofit loss curves are pretty similar between the two. It's actually a little bit higher for the stucco case, and that's because while the retrofit is kind of protecting the cripple wall, that damage that does occur, especially to the exterior siding of the stucco, tends to be a little more expensive to repair than that to the wood siding. But then you could see on the right bar graphs just what benefit is achieved, and that's the numbers that are shown in the boxes there in terms of expected annual loss, how much that's being decreased by virtue of the retrofit. And down in the lower set of plots there, how much the loss at the 250-year hazard, how much that's being reduced. I should point out we'll be comparing 1- and 2-story houses in a minute. Keep in mind that these percent replacement costs are a function of that replacement cost. So in other words, the replacement cost for the 1-story house is assumed based on the square footage to be half of that for the 2-story house. But even in the case of a fairly robust 1-story stucco house, you could see at that 250-year hazard that the retrofit is reducing the costs by about 20% of the replacement value there. So that's still going to be, let's see, what does that number work out to be, about 5, or let's see, if we take 20% of $250,000, so that's going to be still quite a bit of savings from that retrofit. Okay, now that was looking at the 1-story. If we switch to the 2-story for a minute, those are shown here. We don't see as much difference in the unretrofitted condition for the 1- and the 2-story houses. That's just because there's so much more weight that has to be resisted by that same cripple wall. So the 2-story existing houses tend to be more vulnerable than the 1-story. And we could see that the dash curve showing the benefit that we get with the retrofit. Again, you see a little bit like we've seen with the 1-story house, though, that the benefit for the wood siding, shown in the orange bar plots on the right, is about twice the value in terms of expected annual loss. It's about 60% of the value in terms of the loss at the 250-year hazard, but still a significant savings for both of these cases by putting that the retrofit in. Okay, now I'd like to shift gears and look at a few other parameters, some of the index buildings we looked at. Now, one is in the next few slides, we're going to be looking at comparing the 1- and the 2-story houses with wood siding and stucco. Again, the stucco shown with the white graphic, the wood siding with the beige. But then now we're going to be looking at it also at the 4 different sites. So the Bakersfield is shown in blue, San Francisco in orange, Northridge site in kind of the gray color, and San Bernardino in the yellow color. And in this graphic, we're looking first at the pre-1945 houses. So what's different here is that the interior walls are going to be plaster. And the big difference there is the plaster walls are a lot heavier than the gypsum interior. So this tends to make the houses more vulnerable. This is looking at the probability of collapse of the houses with and without retrofit under that 250-year ground motion. So you can see for the high seismic sites, those not Bakersfield, but the other 3, we tend to get pretty high probability of collapse for the existing cases, and all of those are pulled down quite dramatically by virtue of the retrofit. The one outlier there is a little bit the Bakersfield, which has a lower seismicity, where the unretrofitted cases not quite as vulnerable, still vulnerable against collapse, and that won't, by the time we put the retrofit in there, the retrofit is a little bit over-designed for Bakersfield, that in fact the probabilities of collapse under this ground shaking get very low. If we just contrast that pre-1945 house with the latter house is shown on the right, and again the key difference between these two is just the interior wallboard. So we're using gypsum wallboard in the newer variety of houses. And the key difference there is it's just, I don't know the exact number, but it's quite a bit, roughly maybe 2/3 of the weight or so, or half the weight in terms of the density of that interior partition. So it makes the houses better, the modern houses better performing. But you can see the same kind of trends you notice between the pre-1945 and the 1956 to 70. The collapse probabilities in general go down, both for the existing and a little bit for the retrofit. That was what we were just looking at, was collapse under that 250-year ground motion. If we just look for a minute at the collapse under the maximum considered earthquake ground motion, so this is more the code safety level 1. And again, we're looking at the pre-1945 and the more modern houses at the 4 sites. You could again see that with the exception of the Bakersfield, for the more modern houses with the lighter interiors, all of them have a very high probability of collapse at the MCE, And we could see, dramatic improvements or reductions in that when we apply the retrofit shown by the dash bars. And again, Bakersfield getting very low. The other sites are still, depending if you look across there, anywhere between 10 and up to 50% probability of collapse. In fact, for San Bernardino, for the one of the wood frame houses on the left, still a very high, even with a retrofit, 70% probability of collapse. And that's attributed really to the very high MCE ground shaking in San Bernardino, combined with the fact, again, that the standard plan set is designed for a design ground shaking of 1.5 G. In fact, in San Bernardino, the ground shaking is around 1.7 to 1.8 G, so the retrofit's a little bit under designed there. But nevertheless, still a strong improvement across the board. Okay, now if we compare those same set of houses, but instead of looking at collapse, looking at the expected annual losses, we of course have damage functions for all of these, but just in terms of look at some statistics to look at the expected annual loss. So a few takeaways from this figure. If you compare the graphics that are shown on the left to the ones on the right, you again see the fact that the more modern houses with the lighter interior wall finishes tend to do better. The expected annual losses are less. And again, you see the same trends looking at the Bakersfield, shown in blue, tends to be pretty low to start with, but still seeing in terms of expected annual loss, still a pretty significant reduction in all of the blue plots there by virtue of the retrofit. And again, you see very large savings in all of the other cases. And of course, the expected annual loss, as opposed to looking at probability of collapse at the MCE, the expected annual loss is really affected a lot more by the more frequent earthquakes at smaller ground motions that can cause a lot of damage and even collapses to the unretrofitted cripple walls that's then mitigated by the retrofit. And then this is the last one of this comparison between these houses. This is just looking at the losses at the 250 year, and which is kind of you could translate more directly to a dollar value. So again, starting out with values that are typically with a lot of cripple wall failures on the order of 2/3 of the replacement value and being reduced kind of dramatically for all these cases. Again, the specific reduction is going to depend on the level of seismicity and also how the retrofit is designed with respect to that level of seismicity. So a couple other parametric studies that we did was to look at the effect of cripple wall height, because part of the discussion we had early on in this project was how many variations of this index building to look at, and also whether those variations could be tracked through, say, an insurance market. That is, if an insurance policy is out there, would it differentiate houses between the height of the cripple wall or between materials? So we wanted to understand some of these parameters. So what's shown here, I'll just show it for this kind of the two-story example, is looking at the damage functions for the two-story wood siding house with a 2-foot cripple wall versus one with a 6-foot cripple wall in the unretrofitted and the retrofitted condition. So you can see here what's interesting, a little bit at first counterintuitive, is in fact the taller cripple wall. This is a uniform cripple wall height around the perimeter. It turns out to be a little less vulnerable to damage than the 2-foot cripple wall, and I'll talk about that on the next slide in a minute. But that when we retrofit both of these, that when we go to the retrofitted damage curve, and you can see that's the dashed line that's shown there, that they kind of fall in to be together, basically because the retrofitted cripple wall is getting the two to behave in a more similar manner. Now, if we just compare the effective cripple wall height for the houses at different sites, we see the same trend is coming through as that was shown in the damage functions. Here we're looking at the expected annual loss for the pre-1945 houses. The left set is shown for the 2-foot cripple wall with and without retrofit, and then the right set is shown for the 6-foot cripple wall. And if you look at the unretrofitted case, you'll see in generally less losses for the 6-foot cripple wall. But then when you look at the retrofit cases, roughly commensurate for the 2 and the 6 foot. Now, in terms of why the 6 foot cripple wall turns out to be less vulnerable than the 2 foot one, is from structural behavior. There's like a geometric stiffness, the so-called P delta effect, that tends to be it's inversely proportional to height. So when you have a shorter cripple wall, it actually, for a given weight of a house, you have a larger negative stiffness associated with these P delta effects. Also, if you look at the wall failure mode and the ductility of the walls, it turns out that the 6 foot cripple walls have more displacement ductility than, say, a 2 foot one. And then if you look at earthquake displacement demands, it's not just forces from the earthquake, but the displacement demand. Again, if the taller walls tend to have a little more ductility, that a given earthquake displacement demand doesn't do as much harm to them as for a shorter wall. I should point out that the trends we're seeing here for this wood siding was true for the other variants if we looked at stucco and so forth. And then there's a whole other number of factors that one can consider. This cripple wall height is just being one of them. You could think of the condition of the house and the foundation. In general, we're looking at houses that are in reasonably maintained condition. We're not looking at a case of a totally deteriorated foundation. There's other variabilities that can occur in houses. Roof type is one of those, but you could imagine flooring and other aspects that could, for any individual house, could be different than these indexes that we're looking at, the index buildings that we're looking at. The quality of interior finishes, which could affect the repair costs. Again, we've kind of gone with sort of average values here. And also our index buildings have a fairly regular, although representative plan and elevation, and obviously houses with other irregularities could behave differently. But nevertheless, we feel this gives a good, the damage functions we prepared and the statistics we've seen here, kind of a good representation of the inventory of buildings. Another variation we looked at is T111 siding. So this is another type of wood siding, but it's the panelized wood siding. And here we're comparing it on the left side, the T111. This is the loss at the 250-year ground shaking, to the horizontal wood siding. And you can see that in general, the panelized siding tends to perform better in the unretrofitted case and also in the retrofitted case as compared to the wood siding. And if you could think about the 3 exterior finishes that I've talked about, horizontal wood siding, stucco, and panelized siding, that probably the panelized and the exterior stucco perform more similarly as compared to the wood siding. Okay, the last thing I'd like to look through is the stem wall variance. So as opposed to the cripple walls where you have where the cripple wall is, say, wood framing with either stucco or the wood siding that's kind of bracing it, if you will. The stem wall, these are ones that have either a raised concrete or a masonry wall, and the first floor framing sits directly on top of that. And you see some examples of the failure modes that have occurred in stem wall houses. Now, one of the assumptions we made after looking at some numbers and looking at damage reports and so forth is that for these stem wall houses, or the stem wall condition, that the failure mode is really going to be kind of a damage and sliding type failure between the first floor joists and the sill connection. So the failure is not the sill plate sliding off of the masonry or concrete wall, but rather it's going to be the failure between the sill plate and the joist framing above that. So one of the things we had to develop for this was then, apart from all the modeling we did for the cripple wall house, would be how do we model that kind of sliding damage failure between the joist and the sill plate. And basically we have kind of a sliding spring there where the resistance is providing by 2 things. One, toenail between the joist down into the sill plate, combined with the friction, that is just the weight of the exterior walls that are sitting on there that are providing some friction resistance. We also then had to develop damage functions, because again, this was a damage state that was not recognized in FEMA P58. So we have 3 damage states there. I won't go through all the details except to say the first 2 damage states are when you have a moderate amount of sliding that occurs at that interface that can be repaired. Damage state 3 is when you get enough sliding where you start to actually slide off of the stem wall. But we felt that wasn't as dramatic a damage as failure of the cripple wall. So we have a dollar amount associated with that damage for all three of these damage states that's carried through the calculations. Okay, and this just shows an example of the repair cost for those three damage states. This repair cost described in terms of percent replacement value. We actually calculated the specific dollar amounts for these, but if we normalize those, you could see for the first damage state in green is pretty low, and when you get up to the other ones, higher amounts, but that even in the worst of these cases, we never get up to what we assume is failure of a cripple wall being 67%. Some of these approach that, but not quite that degree for that third, the most severe damage state. Okay, and these are the damage functions that we got for the stem walls. This is for the one-story case. So shown on the left is the existing condition, on the right is the retrofit. And on the left, we see that most of the total damage is associated with that stem wall vulnerability. In some cases, we also get damage to the superstructure. But then, as shown on the right, once we retrofit that all of the remaining damage that would occur into the ground motions really occurs in the superstructure once we've fixed that vulnerability at the sliding condition. Now, interestingly, for the two-story houses, we didn't find as much of a benefit of retrofitting the sliding condition at the stem wall. And that's for a few reasons here. First, if we look at the left slide of the existing condition, we can look at the total loss, and it's a function to somewhat of the stem wall sliding, but also just of damage that would get by the stem wall into the superstructure of the house. So that pie chart shows kind of the stem wall shown in yellow, but then the other failure modes that are occurring up in the superstructure. When we retrofit the stem wall, we actually kind of push all the damage up in the superstructure. And again, for these two-story houses where there's still a vulnerability at that first floor framing, because it's carrying all the way to the second floor, we still get a fair bit of damage there, where it's kind of a toss-up between the two, whether, what amount that retrofit, how much it's helping, but it really depends on the strength of the superstructure. This is, though, a topic that we think that there could be further research to look at kind of characterizing that sliding failure at the stem wall in addition to the strength of the superstructure. So this just comparing the loss is at the 250-year ground shaking for the pre-1945 and the more modern ones. And again, the pre-1945 tend to be more vulnerable because of the heavy superstructure. And we see there's clear benefits that are occurring in the one-story houses. And again, the two-story houses, it's a little more of a trade-off because of the inherent vulnerability of the first story that's not affected or not improved by the retrofit. Okay, so I'd just like to wrap up in a couple of slides here. So there's a lot of data and information we showed, but just some general trends, and I can't attempt to summarize a lot of the statistics from the different houses. But if you look at the unretrofitted cripple walls, that I think what came out of our studies is kind of consistent with intuition. The wood siding, houses with wood siding tend to be worse than houses with stucco or the T111 siding, and that's because of the lower strength of the wood siding. Two-story houses tend to perform in the unretrofitted worse than one-story. That's just due to the greater weight of the house. That also translates even more to, if you look at the older houses with plaster interiors, are worse than the houses with gypsum wallboard. And that the shorter cripple walls were actually a little worse than the 6-foot walls. In terms of then the greatest benefits of the cripple wall retrofit, that the wood siding two-story case, that's the one that kind of has the best benefit. But even in all of the stucco cases, there's quite a bit improvement. And again, you tend to find more benefit for the two-story houses. As you go back and look at these the losses in terms of percent replacement value, remember that the two-story house replacement value is twice that of the one-story. So even if they have kind of comparable percent replacement costs, that for the two-story, that's going to translate into more dollars. And of course, the benefit depends on the seismicity. At the low end, if you looked at a one-story more modern stucco house in Bakersfield, you know, the retrofit's a pretty marginal improvement. But then on the other hand, if you go to the two-story wood siding in a site like San Francisco or Northridge, that's where the benefit is the largest. A couple other conclusions or observations. You know, the stem wall retrofit I described were the dominant failure mode that we're assuming between the sill plate and the floor joist. You know, we showed consistent benefits in the one-story house, consistent benefits of the retrofit. For the two-story house, I think that's an area that could, at least based on our results, not showing a clear benefit, but that could certainly be subject to, you know, further review and further testing of that sill plate connection. And the last thing, I think in the next segment, we're going to talk about future research studies, but briefly, if we look at the study that Dave and I did with the information from everybody else, there's clearly more opportunity to validate the results we've gotten through post-earthquake, a systematic look at post-earthquake reconnaissance, what the damage, claims review. We could improve our modeling with data from both the field and laboratory testing, maybe testing of existing houses that might be slated for demolition, to do some testing on those. Understanding better the inventory of the building stock, we saw quite dramatic differences in terms of losses depending on the finished materials in 1- and 2-story, but just to understand better for California as a whole, what is the building stock that's out there in the different regions of seismicity. And finally, the last point is that I think as I mentioned, we developed 125 pairs of these damage functions, and we didn't even look at all the parameters one can look at. You could imagine that in the future trying to maybe characterize these in a more parametric sense rather than having discrete curves, other ways to kind of parameterize these, or perhaps have a statistical model that can facilitate looking at large inventories of buildings. Okay, so I think I'll end it there. I think Evan showed this slide yesterday, but again, just really conveying the key point that, you know, if you look at a characteristic earthquake, the losses and the savings that can be accrued by retrofitting is quite dramatic and certainly well exceeds any cost of these nominal retrofits to the cripple wall or the sill plate. Well, thanks for your attention.
Thank you very much, Dave and Greg, and for this presentation about modeling with the integration of data from the damage repair workshop as well as the experimental testing program. To our attendees, we apologize for the audio hiccup at the beginning of this presentation, which we found out later was actually caused by a power outage in central New York, where Dave was joining us from. So we're not immune. Please do submit your questions in the Q&A button at the bottom of your Zoom screen, and we'll address them at the end of this session. We'll now hear from Evan Reis, structural engineer, who'll talk about the comparison of results from this project's analytical models and results from industry catastrophe models. Evan, please.
Okay, thank you very much. It's a pleasure to be here. It's a pleasure to work with Greg and Dave on this project. The amount of work that they did, Dave in particular, was just extraordinary. And also the work that Bret did with the claims adjusters, I think, is something that really has never been done before. So I really appreciate working with them. I'm going to talk a little about, I presented some of the results yesterday, just sort of the key findings. But as I mentioned, let's see if I can get control of the screen here. There, okay, is that, you know, obviously the primary objective of this project was, as Greg just discussed, to quantify the benefits of retrofitting these homes. One of the ways we sort of calibrated or, you know, checked on how this would compare with industry models was to have a process by which we did a sort of a semi-blind study with the three large catastrophe modelers, AIR Worldwide, RMS, and CoreLogic. And the goal here was, you know, not to try to match anything. I want to be clear that our work was independent. The peer CEA project work focused on, as I presented yesterday, and we've been presenting through this project, existing research, the analytical models, the testing, the work we did with the claims adjusters. But nevertheless, we wanted to see what kind of comparison we would reach with industry models and try and understand where there are differences, why those differences might exist. So again, these are the three modelers that we worked with, and as yesterday, I want to just express my thanks for their really gracious help and time that they spent, and a lot of good discussion that we had. One of the challenges, of course, with doing a comparison with proprietary industry models, all three of these companies have their proprietary models, is to protect their intellectual property. And one of the big pieces of their intellectual property are these damage functions, or these vulnerability functions, as we call them. Remember, Greg presented these vulnerability functions, which were a measure of the building damage or repair cost, loss, different ways to use that term, as a function of the ground motion intensity. So the spectral acceleration at some period, or the return period for a given site. And those, in fact, are the highly coveted pieces of information that each of these loss modelers have. So the very simple way to do this comparison would literally have been to have the damage functions from the loss modelers and simply overlay them with our damage functions, and then we could compare very quickly, how they look. But since that would have opened up the IP, we had to come up with a process that protected those damage functions. And so what we ended up doing, and you saw this, you've seen this term throughout. Dave and Greg really presented it, this term equivalent annual loss or expected annual loss. Sometimes it's called the average annual loss. And you get the average annual loss by integrating the vulnerability function over the hazard curve. So if you have vulnerability, which is loss as a function of ground motion, and then you have ground motion as a function of annual frequency or return period, you can integrate that and get a single number, the equivalent annual loss. And with that single number, what you cannot do is then reverse engineer and calculate the damage function. So we agreed with the loss modelers that in doing this comparison, we would compare the equivalent annual loss, or the average annual loss, between our models and their models. And then we also agreed that we could pick one return period. And so you saw this also, Greg presented a lot of this, the loss in a 250-year earthquake. That number, 250 years, was sort of representative of a large earthquake, a large high return period event, but it was also the one return period that we agreed with the modelers they would also show us on their damage function. So I'll describe that in a second. So then, of course, it was also important to make a comparison to match the locations and the building types with the loss modeler. So I'm going to spend a little time right now talking about how we sort of matched the buildings so that we knew we were comparing as much as we could apples and apples. So the way these industry loss models work is they do something similar to what we did. They have modifiers on their buildings that represent the characteristics of the house, just like we did. 1-story, 2-story, wood, stucco siding, ages. These are the things that obviously affect damage. Now, when we evaluated the buildings, we, of course, used the analytical modeling, trying to represent in computer format the characteristics of those buildings. The insurance modelers typically use empirical data. So they will gather empirical claims data, and they will bin it into age groups and stories and these other types of modifiers. There are certain modifiers which are sort of essential to get, and those are called primary modifiers, and they typically have the largest impact on performance, and they're the easiest typically to obtain. And I'll describe those in a second. Other modifiers, secondary modifiers, have a smaller impact. They may not be as easy to find or identify in the building, but they typically also have a smaller impact on the building. And so this combination of primary and secondary modifiers is what we focused on. So the primary modifiers for all the modelers, for all the 3 loss modelers, really focus on the location of the building, which identifies its seismicity and its soil profile, right? You know, as Greg showed, buildings in Bakersfield have a much lower seismicity than buildings in Northridge, so they may perform differently. Number of stories is another primary modifier. About 95% of houses in California are 1 to 2 stories, but the models typically allow for 1 to 3 stories. And then the age of construction. The age of construction represents different types of construction codes, characteristics, the types of the more common types of siding and other things that would be on these houses. And each of the modeling companies has their own view of the appropriate bins of age, but we were able to come up with an age group that generally matched pretty well with the loss modelers. Then the secondary modifiers, again, and I should go back and say that all of these things are something you should certainly be able to get for a house. Obviously, the location, its address, the number of stories, and typically you can get the age as well. Secondary modifiers are sometimes a little bit more challenging to get, but nevertheless, they can typically be developed by the underwriter. The siding material, and Greg presented this, wood, stucco, brick, other types of siding materials. The foundation condition, we focused on cripple wall homes and stem wall homes. Because that was the intent of this project, not to work on slabs on grade. Building shapes, L-shaped buildings, T-shaped buildings, rectangular buildings, and then other elements of the building like chimneys and porches. We specifically excluded that from this evaluation because, again, we wanted to focus on the benefits of the cripple wall retrofit. So we didn't focus on other ancillary characteristics, but these are often things that are in the models. And then typically whether the building is upgraded or not, or retrofitted or mitigated. And each of the models includes that as well. Oops, I'm going the wrong way. Hold on. I don't know why that's in there. Oh, okay. Okay, so this semi-blind study. So how we did this. So again, David and Greg showed this graphic here. This is the typical vulnerability function for a building. You see you've got wood and stucco, 1-story house, wood and stucco, unretrofitted and retrofitted. Okay, now ideally we just love to be able to take the same things from the loss modelers and overlay it right on those curves. That would be the easiest way to simply compare them. But yeah, those are the damage functions. But since we weren't able to do that, we created this sort of way to calculate the equivalent annual loss. So again, each of these levels of ground motion, the spectral acceleration here, has an associated return period given the location of the building. In some places, you'll get a higher ground motion with a lower return period, like in San Francisco. Other places like Bakersfield, a lower ground motion at a higher return period. Okay, and that return period, 1 over the return period, is the annual frequency. And so by integrating the vulnerability function over the sort of return period or annual frequency function, you get something called the average annual loss, or the equivalent annual loss, or the expected annual loss. There's different ways to categorize it. And so that's what we ended up producing. We ended up producing for our results, and the loss modelers did the same thing, this AAL or this EAL value. And then we also picked one return period, 250 years, where they would give us that information. So with those two pieces of information, we could make a good comparison between the models, but we weren't able to sort of reverse engineer the damage functions, or somebody reading the reports couldn't reverse engineer them. We picked 4 locations. Sylvia talked about this yesterday, representing different areas of seismicity in the state. We gave these locations directly, you know, the soil profile. We assumed Class D soil everywhere, and we gave these lat longs to the loss modelers. All right, so eventually we decided, we were going to, as Greg mentioned, we had couple hundred different building types that we ultimately considered, but we had, in this study in particular, we wanted to compare a subset of the buildings where we could match the CAT modelers' primary and secondary modifiers. Okay, and so we boiled it down eventually to 48 index buildings, as you can see here, 3 different age groups, 2 types of siding, 2 heights, 2 foundation conditions, and 2 construction conditions, retrofitted or unretrofitted. And these would match, you know, perfectly with the CAT modeler's own index buildings, if you will, their primary and secondary modifiers, with the slight exception of the age groups. Again, I mentioned there were some slight differences between the age groups of each of the modelers, but generally speaking, they were pretty close to these numbers here. So these 48 buildings became the comparison set that that the CAT modelers ran to give us the AAL and the 250-year loss, and then that we ran as well. So let me jump into some of the results that we found here. The most important piece of information that you should take away from this is that the unretrofitted condition, we show substantially more loss than the CAT modelers do. And Greg's talked about this. The reason behind that is for the collapse of the cripple wall it happens at fairly low ground motions. And so you can see the average annual loss here. Blue will always be the peer results. Green will always be the average of the CAT modeler results. The solid bars are the unretrofitted condition, and the hashed bars are the retrofitted condition. So you can see it jumps right out immediately that there's a lot more loss in the unretrofitted condition comparing the solid blue to the solid green lines. But you can see that there isn't as much difference with the retrofitted conditions. There's a substantial improvement with the peer CEA models. There's not very much improvement shown with the CAT modelers, but in that case, they actually come to more comparable results. So you can see here, again, not a large improvement shown by the CAT modelers, and this is one of the key findings that we had, whereas we get a very large improvement with our models. This compares siding, okay? So now you have 1- and 2-story homes all combined, but you have wood siding, you have all the age groups combined, but you have wood siding versus stucco siding. Again, you can see that the unretrofitted conditions have substantially more loss, although it's really more in the wood-sided houses. The stucco houses, it compares a little bit better, at least with the CAT modelers. But again, when you get to the retrofitted condition, you can see that the comparison in performance is better. But again, this really all has to do with, as Greg showed, the potential collapse of the cripple wall. Okay, so now we're comparing across all ages and cladding types, the 1 versus 2-story homes. And you see what seems to be sort of an obvious bump in losses, a large bump in losses for the unretrofitted homes, for 2-story homes, and that is a function of the mass. In the unretrofitted condition, you have these weak cripple walls, and you're doubling the mass of the building. What we found typically is that the cripple walls don't get stronger in older designs because there's a 2-story home. It's not like they used 4x4 studs or 2 layers of sheathing. Okay, so it's essentially about the same capacity with twice the mass. So the losses are substantially more. Whereas there isn't that much of a difference shown by the catastrophe modelers, only from about 0.22% average annual loss to 0.29%. So an increase of 20% or so, whereas with our models it's about 80% increase in damage. So again, another interesting takeaway. But again, as we retrofit the buildings, you can see the comparisons get much better. Okay, stem wall versus cripple wall. Now here's an interesting result. Craig was very showed you that it really, again, I'll reiterate, is the stem wall, the cripple wall condition where you have collapse of the cripple wall being the biggest issue. And you can see that here. The stem wall houses perform quite well. And in fact, retrofitting the stem wall houses, doesn't improve their average annual loss by a lot, but it obviously does with the cripple wall homes. homes. And you can see too that the stem wall homes compare very favorably all the way across the board with the loss modelers, whereas again, we have this issue with the cripple wall. So if you consider the level of, well, what has come out of this is that what we're seeing is that I'll show this in the summary of the results, is the CAT modelers tend to underpredict damage relative to what peer CEA is predicting. Yeah, okay. Okay, so here, and you know, our working group 6 report has all sorts of figures, so it's got as many figures as you could possibly want. And of course, the database of the information is generally available as well, although it's, you know, it's anonymized appropriately. You can see here, these are for raised foundations in the unretrofitted condition, average annual loss. And you can see again, so this would be a wood cripple wall, a wood cripple wall with either stucco or wood siding. You can see a substantial difference in performance, as Greg mentioned, whereas there's not that much of a performance difference in 1-story versus 2-story homes for the from the loss modelers themselves. This is the 250-year event, so I've been showing you average annual losses. 250-year event, again, you know, pretty substantial differences between the cripple wall condition, the raised cripple wall condition for 1- and 2-story homes versus the CAT modelers. This is a comparison of the retrofitted and unretrofitted condition for this is across all age groups, for 1-story houses and 2-story houses with wood and stucco. Obviously, since the 2-story homes perform worse than the 1-story homes, and the wood cripple walls perform worse than the stucco cripple walls, you can see the benefit of retrofit is substantially better with the wood cripple walls. And again, the benefits are substantially better than predicted by the catastrophe models. You can see the difference between the solid and the hashed bars is much less across the board for the average of the CAT modelers. You know, you're getting maybe a 20% benefit for retrofitting the home, whereas with the peer project, you're getting, you know, a 70 to 80% benefit for retrofitting. So this was an important consideration as well. Similar kinds of benefits at the sort of the high return period event. So the sort of the big one, if you will. This is the kinds of results that we were getting. Again, much clearer benefit for retrofit than would be indicated through the CAT modeler. So to jump into the key findings in my last couple slides, as I said, this issue when you have a 2-foot cripple wall, unretrofitted, the modelers consistently estimated a lower damage of both average annual loss and at the high return period across all the age groups, heights, what have you, with respect to the peer CEA models. So our analytical models coupled with the testing really showed that the collapse of the cripple wall is an important consideration that may not be properly or fully accounted for in the models. Both groups obviously estimated more damage for a 2-story home than a 1-story home, but we determined that the mass difference was pretty substantial, and so the difference in performance between 1- and 2-story homes was more pronounced than the difference between 1- and 2-story homes that the modelers predicted. Let's see. Okay, so for the stem wall conditions, the peer project really estimated very low damage. And so in this case, the CAT modelers predicted slightly higher damage in for the stem wall conditions than did we. And part of the reason is that, you know, part of our testing and research on these unbolted stem walls, you know, where you have a sill plate that isn't bolted, we found that the wet set condition where these sills are maybe spiked with nails and then set into the wet concrete actually provides almost as much resistance as bolting itself, so that you really, you get this failure mode where the joists pull away from the sill plate itself, and so there's still a substantial amount of strength. In the retrofitted condition, however, we both found fairly good agreement, the modelers and our project, and that really, I think, goes to show that you don't get a lot of damage in the upper stories when you have the retrofitted condition, because there are a lot of interior walls, there's a lot of redundancy, and so maybe, these houses are really pretty good, all things considered, once you've retrofit the cripple wall. Okay, oops, let me go up one more time. Okay, the fifth finding is, and this I mentioned briefly yesterday, we show, the peer project showed a consistent improvement in performance with age. So the losses were higher for the older houses and lower, for the 1945 to 55 houses, and then lowest of all from the 1955 to 70 houses. And really the reason for that is purely analytical. It has to do primarily with the weight of the building. The oldest homes use lath and plaster, which was very heavy. It's a bit stronger than gypsum board, but it's heavier than it is strong, and so it adds more damage. And the newest houses all had gypboard, and the middle group of houses, we just used a half and half kind of thing, assuming that some of the houses would essentially be gypboard, some would be plaster. Okay, so there would be a natural reduction in the losses, but for the most part, all of the CAT modelers show that the losses are highest for the oldest houses, and they drop down for the 1945 to 55 houses, but then they go back up again a little bit for the newer houses, 55 to 70. And that, we did a study several years ago with the CEA, peer did, and we found that it really may have to do with how construction practices were going, less union labor, sort of quicker construction, less sort of trained craftsmen. And so until the building codes really started to catch up maybe with the poor construction practices or the less trained people, damage ends up getting a little bit worse in that sort of 55 to maybe 1980 phase. And then another last key finding was that the modelers really didn't show much difference between stucco and wood in the cripple wall, whereas we showed a pretty substantial difference. There was much better performance when you had a stucco house, because it really does add a lot of strength. It's heavier, but it adds a lot more strength. So what we found is that retrofitting stucco homes is less beneficial than retrofitting wood homes, because the wood homes unretrofitted have substantially more damage. Okay, so that is all I had to say, but except that I did want to reiterate one thing that both Bret and Greg mentioned in the project as in terms of sort of future goals. And they both mentioned this idea of working more collaboratively with the insurance companies to get claims information and underwriting information. And I hope that the modelers will agree that this was a successful working together, that we can play nicely, researchers can play nicely with the insurance industry. And, there is so much more we can learn if we have access to anonymized inventory and claims data. And so I hope this really will encourage the insurance industry to be more forthcoming and collaborate with researchers going forward. Okay, that's all I have.
Thank you so much, Evan. To our attendees, you've received a lot of rich information over the past hour and a half. Please do submit your questions at the bottom at the Q&A button. Meanwhile, I'd like to invite Bret, Dave, if you are available, Greg, and Evan to remain, for you to remain with your video images and unmute themselves. We have time maybe just for one question, but what we will do is we will save the other questions and defer them to the afternoon, where we have more time to discuss clarifications and questions. So let me get to that. This comes from Charlie Scawthorne, and Greg, you appear to have settled on $200 per square foot replacement cost. How does this square with costs coming out of the Santa Rosa fire, like the Tubbs fire, of about $400 per square foot? Or, how do we account for variations in cost?
Yeah, well, that's a great question. It's an obvious one that we've been asked before. I think the most straightforward way to think about that is that all of our repair costs, which again, we started with the ones from P58, and then we also kind of validated those against the adjusters workshop as Bret described, were associated with a replacement cost of $200 a square foot. So I think and then when we describe our loss functions in terms of percent replacement value, our implied assumption there is that if there's an escalation in replacement costs, and that could be due to just location of a building, San Francisco versus somewhere in the country, or demand surge after the Tubbs fire or after an earthquake. So we think that if there's an escalation in replacement costs, that would translate into also repair costs, such that the percent replacement values we think is a more kind of steady measure of losses.
Thank you. At this point, I'd like to hand it off to Janelle, who will take us out onto the break. We did have a little bit of a sound glitch, but as I said, we have a handful of questions now that we'd love to defer to the afternoon to this very same team as well. So Janelle.
Thank you, and absolutely, what excellent presentations. I really appreciate it. Bret, Dave, Greg, and Evan, thank you so much. Really complicated, and I really look forward to having a little bit more in-depth question and answers this afternoon. So we are going to take a 10-minute break. So I'm going to steal a minute from the next session and give it to them in lunch. So at 11:11, please want to make sure you give you a chance to check your email, but please do come back, because the next session and the following sessions are really going to be very interesting. So thanks. See you soon.